That must go there. And that does.
That's it.
Gulliver's Laws.
That
must go there.
Yeah, that's right.
That must go there.
Royal Institution Christmas Lectures. Lecture 1, The World of Captain Gulliver.
Well, let us begin with an experiment. Will you uncover the apparatus, please? Well, it resembles the Queen's penny anyhow, but perhaps it's not quite the same. How about a measurement? Can we measure that penny? Two-man to a ruler? Huh?
About 1.2.
1.2 inches, I suppose. Are you sure about that?
Yes.
All right, thank you. I guess you'll just take those away then. Well, that's not the only way to measure a penny. In fact, I think that must leave us with a small amount of doubt, because it looks bigger than what I normally regard as 1.2 inches. I wonder if someone would help me measure it in another way. Can you do that? See how many of the pennies of the realm will fit across it. It's pretty round, so if we get the number that go across in one direction, I think we can say it's about the same in all of those directions. How many did you get?
12.
Oh, very interesting. 12 pennies across. How many thick is it? Pretty level, is it? Does everyone agree? Who can? Looks right to me. Thank you very much. Well, we can see that that's like a penny. It's a disc of copper, of course. If it was a minted penny, it must be a penny minted in the land of the giants, for it's 12 times as far across and 12 times as thick, and it probably has other properties which are different from the normal penny. One way to tell that, I can try another trick which brings out something more about a penny than its geometrical size. Let me try this, for example. I will spin it. Will that penny spin? Okay. It spins very well indeed. Thank you. Thank you. Thank you, Bill. It's done its job. This is a beautiful and scarce little book I have in my hand. It's the first volume of Gulliver's Travels in the second London edition, 1731. Gulliver's Travels is a remarkably successful book, as you know. I hope many of you have read it recently. It sold out the first edition in a flash, and the second edition was printed promptly. I think the second edition myself is the best for book collectors. It has beautiful text with that fine 18th century script, and it has the drawings which we are used to for many, many editions. But the first edition sold out so speedily that it had to be printed and printed over and over again. You know, it was anonymous. The book was put out as though it were written by a certain Lemuel Gulliver. Dr. Gulliver is indeed the hero of our course of lectures, and they are entitled Gulliver's Laws. I don't think he discovered them, but he made them his own by having the adventures described in the book. Of course, the gossips of London soon knew it was Jonathan Swift who had written the book. The word went round. All those elegant ladies who were the friends of Dean Swift wrote him nice letters, poking fun and talking about their experiences with large and small people, and the whole thing was a kind of public joke. But a very beautiful book it is, a book which is both entertaining and serious at the same time. It has to be regarded as part of science fiction in the first place, because it tells us really splendidly how it is to see a land which has small people and a land which has large people and many another strange adventure. But it was not at all a book of science, and indeed it represented an honest effort by an author to describe such a world, but that was not his main interest. His main interest was the nature of man, and he made the little people show that which is petty and small and mean in us. And he made the big people large-hearted and large-spirited to show that which is generous and good in us too. And throughout the book, he has, as many authors of science fiction, a genuine try at showing mankind, whom we are, what we're like. But it's a beautiful book, and I want to read from time to time from it to suggest that what we're doing here is in that spirit. Not always will we agree with what it says here. Much of what it says could not in fact be true. But that is the burden of our course of lectures, to understand how deep indeed size is built in to the physical world. I shall read a bit from the large land, because we have just been through an experience such as Gulliver might have had among the giants if he worked at a school desk. I fell into a high road, for so I took it to be, though it served the inhabitants only as a footpath through a field of barley. Here I walked on for some time, but I could see little on either side, it being now near harvest and the corn rising near 40 feet. I was an hour walking to the end of the field, which was fenced with a hedge of 120 foot high. There was a stile to pass which had 4 steps and a stone to cross over when you came to the uppermost step. It was impossible for me to climb this stile because every step was 6 foot high and the upper stone above 20. He felt like my ruler team, who had a hard time if they had to go to school with that ruler instead of this one. Now, the discussion of size has necessarily to be in parts mathematical. We are talking of form, geometry, size, shape, figure, and we shall pay attention to this. Not because I know it is Christmas holiday, not with difficult mathematics, but mathematics of Gulliver himself, and I think it will go well. But I would like to begin by discussing just a little bit of what was in the minds of the people in the 18th century. What we still believe today. I have tried to make all those triangles alike, similar, assume that I have done so. In that case, do they all have 180 degrees? Of course. They all satisfy the rules of Euclid. No one would doubt, no one would imagine that the size of the diagram could influence the theorems of Euclid. That is the nature of the geometry of Euclid. That is the nature of similar proportions, but that is not the way the world always works. Only sometimes does it work that way. In the shape and size of the ruler, say, it would work well. That is not the whole story. Let me show a very simple example, just to remind you of a geometry which is not the geometry of Euclid, in which the proposition that every triangle is 180 degrees simply does not hold. And it's a familiar and an easy geometry, which we know all the time. Imagine this balloon to be a sphere. I will work on part of it only. It will be rather spherical. If I draw a small triangle, I think you will believe that nearby, if I look at it closely, it is very near a flat surface, and my propositions will not be much different if I work on the flat surface. But if I draw a large triangle, a line like that, and let me draw a nice right angle here. It's a good right angle. And a nice right angle here. That's a good right angle. But if I continue with straight lines, of course, on the flat plane I never meet. But here I make a splendid triangle. Well, I submit, if they're 90 degrees here pretty close and 90 degrees here pretty close, I've used up the 180. There must be something to assign to that triangle. Of course, you know very well the theorems of Euclid simply do not apply in the non-Euclidean geometry of a sphere. And what determines whether they apply or not, how closely they are approximated, is one thing and one thing alone. Namely, is the triangle large or small? And when I say large or small, I say with respect to what? And of course the answer is quite clear. Large or small with respect to the sphere. If they are tiny triangles, as we draw triangles compared to the great globe of the Earth, then Euclidean geometry works. If they are huge triangles, like the triangles made on the sphere by the lines of longitude and latitude, then Euclidean geometry is no longer true. Different rules, different propositions hold. And the key is a size that has been built into the geometry by the size of the sphere, the radius or the diameter of the sphere. In the same way, but intricately, very deep inside matter, by the atoms, by the forces of nature, by many and other phenomena which we will expose one by one, size is built into the things of the natural world. And it is not always true, though sometimes it is true, that a small penny is like a large penny, only smaller, and so on. The functioning may well be entirely different. And that is the burden of most of what we have to say. For example, let us look, to begin with, at an object or two which is man-made. You know that London and all great cities today derive their light and all the electric power we depend upon from large turbo generators. Generally, steam is raised, high-pressure steam in many turbines spins an enormous object like that. Just to examine the look of the man there, I think you will agree this is no small machine. Mr. Coates, would you bring the turbo generator in? Clearly, it couldn't be done. The object weighs several hundreds of tons. It could not be supported, could not be brought into this portion of London. That is a truly Brobdingnagian machine, though it was made by our size man. Now, the rules of the game, the operation of such a machine is not the same as the operation of a spinning electric machine that we might have in your electric fan or in any toy device that might be driven by an electric motor. For example, we have here a close-up of the machine. Well, put this out of the way. And here you see a single piece, the rotating part, enclosed in another copper coil, and we have a small section of the copper coil coming out of the stationary part of the machine here. This is the object. It's just a small bit of the machine, obviously, and yet it makes a point, because you will perhaps notice that on the end of this is just a piece of wire in an ordinary electric motor. On the end of this wire, there are rather carefully fashioned channels. Those channels carry water, which cools the coil of this great machine in operation. And such water cooling is indispensable. Indeed, the whole machine runs in an atmosphere of hydrogen, not in ordinary air. The great difficulty of maintaining that is worthwhile in terms of the different performance of the machine. So that is the one indication of how large scale, in this case the large scale of engineering, manages to show its influence on the operation of machines. Now, Gulliver, of course, was not only in the land of the giants, but he was also in the land of the dwarfs. And we must say something about the other side of his voyage, about small machinery. And I chose to show the rotating generator because of a charming story which really happened a few years ago in Pasadena, California, to an associate and friend of mine, Professor Feynman of Caltech in Pasadena, who conceived the idea, and putting it in his rather slangy way, of giving a $1,000 prize to the first guy who would make an electric motor that would work and would all be contained in a cube 1/64th of an inch on a side. 1/64th of an inch. That's very small. I can't draw that in the blackboard. The smallest dot is far, far larger. Indeed, the full stop in a piece of printing of ordinary size is about that size. And he wants a motor to be constructed entirely within that space. Of course, it could be as thick as it was wide, as it was high within the cube. The lead-in wires can come out, and the generator supply the current can be in the outside, but the whole motor, to satisfy the prize, must lie within. Well, he made the announcement and gave his own money for this purpose. He was somehow very enthusiastic at the time, and he was trapped into it. And in fact, he offered the $1,000, which he was willing to pay. Los Angeles is a great city, and it is particularly strong in the precision industries, optical and mechanical precision industries, because of aircraft, electronics, and so on, films. Not many of those people, however, seem to be interested at first. But all the other persons who dwell in the city, all sorts of collectors of all sorts of odd items appeared. A man came and offered him a clipper ship made in a quart bottle. Another man came and offered him a cabin, a log cabin like that of Davy Crockett, made of matchsticks, and so on. Well, these were mere jokes. He was not interested in just anything curious and small. He was in fact interested in precisely what he asked for. And he began to give up, because after 10 or 20 persons had come with all sorts of strange and curious objects, none of them understanding in the least what was the nature of his interest, he felt that he was never going to see someone who was going to pick up on the prize, and the whole matter was over. It was a good joke for a few weeks' time, and that was all. And then a young man stopped at his door one day and said, "I've come about the motor." Feynman explained, "Well, so many people have done that, I really have no more confidence in the art. I have no time to discuss it. I'm sure that you haven't done it." He said, "But, sir, I have done so. I have exactly met the specifications. I have produced an electric motor inside a cube 1/64th of an inch on edge." Well, with that explicit statement, what could the offerer do but listen? So he listened, said, "All right, I'll show you." And the man produced then, much to Mr. Feynman's dismay, a large box very like that box. And Feynman's heart sank, because that box is far too big to contain a 64th inch motor. And why would you bring such a big box? And then when he looked into the box, as you were looking into it, I will take out the contents. Here, in fact, is the motor in its container, very big container. Here is what is really in the box: a microscope. Does it make sense to bring a microscope if you want to display your handicraft of a 64th inch working motor? It does. You cannot appreciate that motor without some aid to the eye. And that is one of the burdens of this story. The extension of man's senses by instruments is the indispensable quality of modern science. Let me then take the motor, which is here. Now, you're not seeing the motor. This case contains lots of supplies and fittings. In particular, it contains a spinning generator knob, which makes the electric alternating current that powers the motor. The 4 leads here are the 4 posts into which the 4 wires go that carry the alternating current into the motor. Then you'll see a central square, and then a circle. None of those are the motor. And in the tiny disk, in the center of the big circle, that in fact is the motor. And with very good eyes, you might barely see it. But in order to make it really visible, we must do what Mr. McClellan, the maker of the motor, did, and show it under a microscope. Bill, if you please. Now let me say a little bit about the motor while we are at it. Here is the same motor made not of real materials, but what we call a mock-up, or model of simulated materials, to show you the structure of the motor. This one, of course, would not work. It is a foot by a foot by a foot. It's inside a 1-foot cube. The other one is a 64th of an inch cube, and I hope you have come to see how much smaller that is. Here are the coils wrapped on iron rods. These are electromagnets. The generator powers first one and then the other in sequence, and they're changing north and south poles, attract the north and south portion of this permanent magnet disk, which spins a molybdenum shaft in a quartz bearing. I'm discussing always the real motor, on an iron base, and those are the parts of the motor. What do you think? How do you think you go about making such a motor? It's evident that you must work exclusively under the microscope, sometimes with 2 microscopes at once, 2 men working at once to drill some of the right-angled holes that have to be made in fashioning the machine. The machine was made in this way, and it has worked beautifully. This is the second one made in the world, as far as I know. Now, if we may see the picture of the motor under the microscope, you see there's a light, a microscope illuminating, and there's the motor. Now, if you can spin it up, Bill. There's the whole. Now, there it is. Oh, it spins away merrily. Try it again. Give it a good fast one and let it coast down. Very good. You see the rotor. Now, there's no mechanical connection between the wheel that Mr. Coates is turning and the motor. It's purely electrical. Wires lead to those 4 input leads, and there it goes. So the motor really does work. Thank you very much. We have seen a little electrical machinery that's small, and I think the contrast is very nice. It suggests we live in a world which still has some of Gulliver's feelings. But let me point out that there is no use known for this small motor. But small electrical equipment is very much used. Many of you will recognize this sort of equipment, which is a printed circuit board loaded on the rear side, which we will show, with transistors and condensers. The sort of amplifier you would find in an ordinary record player. 10 years ago, if I brought in exactly the same audio amplifier, I would have had to bring in a large tin of metal with 4 or 5 hot glowing valves, I think you say, on top of them. A very different object from this. This one, you see the intricate wiring of the circuit board, and on the other side, you can see the many components which make it up. But this too is large for some uses and for some standards, and today an equivalently functioning device without the container, the protective container, or the leads which we needed for men to assemble it, is here in an integrated circuit glued to the end of a pin, to the head of a pin. And I can put this down, and you see a very small object indeed, and yet that object is an amplifier, an audio amplifier of about the same capacity, about the same performance possibilities as this one. I think we are able to show you an identical one already mounted under the microscope. There it is, and you recognize, I think, the same quality, the same careful drawing of circuitry which was found in the large-scale printed circuit. Now I would like to describe a little bit more of the mathematics of Gulliver. And I think that now the time has come for our next piece of apparatus, a familiar, I hope not too complicated apparatus. Spill them out, Bill. Very good. A set of similar, in fact, of an equal-sized cubes. They may also run under the title of children's blocks, if you choose. Now, I want to describe, quite straightforwardly, some of the simple mathematics of this scheme. Let us consider an assembly of this sort. I'll place out one block and two in a row, and three. I span with my finger there, I span that length, I span that length. It's about as much as I can easily span, and you see I can reach, with sufficient number of blocks and patience, I can reach any length. 1, 2, 3, 4. Let me write that down because it's a good introduction to the more complicated formulae I may wish. The length against the number of blocks in line that's what I may write. And of course, the number 1, 2, 3, 4, and the length was successively 1 unit of length. Of course, it was not. I didn't say what the unit is. I have not said that at all. Those blocks happen to be 2 inches. But no matter what size blocks, it's still true that whatever unit of length I use for a block, I get 1 length there, twice it there, 3 times there, and 4 times there, against 1, 2, and 3, and 4 blocks, respectively. This is the simple statement that the length, let me call it L, is proportional to the number of blocks in a line, let me call it N, and I will use this quantity for proportionality, this sidewise quantity. And the proportionalities are what we're going to deal with very much throughout the course of the next lectures. But length is, of course, not the only property. In fact, it's a rather simple-minded property. Let me try something more complicated. Let me try area. And area 2 on edge gives me an area of 4 blocks. 3 on edge gives me an area, top area, surface area, top, of 9 units. And 1 on edge, 1. 1 on edge, 2 on edge, 3 on edge, but no longer 1 unit of area 2, not at all. 1, 4, 9. Another familiar result, which clearly leads me to the result that the area goes like the square is proportional to not the number of blocks on edge, but the area of a square. Or indeed, if you think it through, of any figure, any similar figures go like the square of the number of units which can reach across it. So this is the first result, this length, the second result, area, and you would perhaps know the answer for this, but let's try to pick up a few. What I'm going to put here, of course, is volume, because volume in our world, perhaps not in the world of the astronauts always, means weight. And let's ask about weight. Volume will go with weight. 1 object and 2 identical objects weigh twice as much as 1, and so on. So let us find out how this will go. And of course, I won't leave the statement incomplete. Let's just check. I'll put it n cubed, perhaps giving away the answer, but we all know this. It's only to get some feeling for how serious these numbers are. Well, it's easy to start, and I will start, but I will need some assistance to finish. 1 cube, 2 on an edge. Well, I can almost do that without too much trouble. Do you think we could start making a 3? And perhaps someone else could help and help us make a 5. Plenty of blocks here. Try making a cube, which is guaranteed to be 2. Here's 1, here's 2, here's 3, here's 4, and 5 blocks on an edge. See how far you can get with that task. And that is clearly the task we have to answer to satisfy this cube law. Now the numbers are pretty good. I can give you a little bit of help. I hope you already begin to notice something that has me worried a trifle. We had an ample supply of blocks. It was clear it was much larger than one block and much larger than the two. We had plenty of blocks. And yet we have a little fight developing here. Can you help out a little bit, Bill? Yes, a few more blocks. Good. A small step. I'm going to write down the numbers on an edge up here, and we'll see what data come in from our contractors. Volume, number of cubes, 1. Here was 8. That's as far as I was able to get, I think. What have you got? Can anybody help me count? What do you have on that one, say? No, the smaller one. We haven't got that yet either. Looks to me 3 on an edge. How many in each layer, then, would you say? 9. And how many layers make it up? 3, so that is 27, and that works fine. And did you get the 4 cube finished? No, not quite. Well, we don't know, but we all know what the answer will be. 4 by 4 by 4, and I think we have the clearest sign of the cube. If the cube law is right, that's why. Thank you very much. You've done nicely for us. But I hope that people have taken the lesson, which is the lesson, the Gulliver lesson, that if I make something similar, the volume, and hence, in general, the weight, goes up with prodigious speed with the cube. And its cube is a rapidly rising function. I say rising and going up, of course, because I'm thinking of graphs. And let me draw the sort of graphs I have in mind. If I draw a length here against number, that was proportional. So it's a straight line graph. 1 for 1, 2 for 2, 3 for 3, and a straight line. If I draw area versus number, it was a square law. 1 for 1, 4 for 2, 9 for 3, and I get a curve like that. And for volume, one for 1 again, 2 gives me 8 way up there, and 3 gives me 27. You see a steep curve rising very rapidly. Nor need we think that the only powers that are of interest to physics are the first, second, and third. Let me observe, of course, this is n, really n to the 1. To make it look pretty, I like formal arrangements like that. And I think you can see n to the 1, n to the 2, and n to the 3 is the way we go. So that is the style of the geometry of Gulliver, and that's nearly all the mathematics we need. We need just a little bit more, which I shall discuss in just a moment. I want to discuss a little bit the ideas of magnitude. Thank you. We can normally note magnitudes also by this very handy use of the exponent. And I will simply quickly remind you that we can speak of millions and millionths, of thousands and thousandths, dividing and multiplying as we choose, using the powerful method to say instead of 1,000, we often say 10 to the 3, simply counting the zeros. Instead of 1 million, we say 10 to the 6th. Instead of 1/10, we say 10 to the -1, and we go up and down the scales as we choose. This magnitude remark is simply to remind you, one doesn't expect it to all appear here. And I'd like to show how magnitudes vary, and of course to show that is not very easy. Remember, instrumentation is likely to be needed for our work. But just to show how physical systems do sometimes behave, here we have 2 rather related objects out of the electronic world. These are condensers, air capacitors with changing plate positions, whose purpose it is to store up electrostatic energy. And the amount of energy they store for given voltages is proportional to what is called their capacity. Here's one with a high capacity and a very similar model object, really just the same device, only made very tiny, has about 1,000th the capacity of this one. But the striking thing is that between this and this object, which while it does not look anything like physically, is an electrolytic condenser. Again, it's a capacitor. Again, it has sets of plates, electrical conductors, in this case very thin aluminum foil, wrapped round inside, kept apart not by a thick layer of air as here or here, but by a very thin layer of a tarnish coating on the foil. Such a condenser has a capacity which is 5 times 10 to the 9 times larger than this one. You see, we're not talking about geometry any longer, but about physical circumstances. And the physics of the interior manages to make such a big range of scale appear in the electrical apparatus. And consequently, we can say that the smallest one happens to have a capacity of about 10 to the minus 12th units farads, notice, and the largest one about 5 times 10 to the minus 3 farads. And that is a very big range just to have sitting on the table, both in visible form. The point being, of course, it is not mere geometry we're talking about, but the electrical properties of a relatively complicated system. Now I would like to proceed to a subject which is still more interesting. Here we have resistors. Again, this is a huge resistor, but it's the same effective resistance as this. In terms of resistance, each is 1 million ohms. Their other properties are quite different, evidently. This one would be all right, that one not all right to drop on your toe. To study length is clearly a principal business of this kind of physics. Here is the fundamental unit of length, or a reasonable approximate copy of it, 1 meter. If I were to multiply it by 1,000 meters, I could not hold it in the lecture room, but I can easily stroll that distance. Thank you. And if I were to do so from the Royal Institution, we've placed just to show you where you may walk if you wish to walk about the center of London. That's a kilometer circle. It reaches out toward Buckingham Palace. It reaches out past the British Museum. And much of the center of London can be reached easily by stretching 1,000 meters around the Royal Institution. Of course, if you were to try 1,000,000 meters, you'd be outside all of England, and 100 million outside the whole Earth, and so it goes. So we have some feeling of the range of length on that side. But the range of length on a smaller scale is not perhaps quite so easy to obtain. And that is, as we have seen, very often the sign that we need something more than our senses to detect. If we've detected 1 meter and we can walk 1,000 meters, what about 1,000th meter? That's easy. 1,000th of that again, 1,000th of that again. How far can we go? There we will call upon the aid of a powerful instrument. And this set of racks is the beginning of that instrument. Very beautiful device. I want to talk a little bit about it. And Miss Hardy perhaps will be so good as to operate it for us. And I will try to talk a little bit about it as she proceeds to make it work. We've got something in there. We've got a duplicate out here. And we should be able to see really very far with this kind of device. Such a device is an electron microscope of a special kind, barely a few years old, invented, developed, and manufactured at Cambridge, England by the Cambridge Instrument Company, and called a stereoscan. And a very ingenious device it is. One pays a price for looking for very small objects in an electron microscope. The price is electrons will not go through air as light does. So we need to make our sample and the electron beam run in a vacuum, whereas the light beam and the sample can be in ordinary air. Here is the vacuum container, the source of the electrons up there, the specimen in here. These large knobs allow positioning of the specimen, and the electronic controls will do what I show a little bit in a moment. Now, the heart of the instrument, of course, is relatively subtle, and I cannot describe it in full detail, but the idea is easy enough. What one needs to produce is a very delicate and fine stream or beam of electrons, and that is made in this machine. And the spot here at the end is so fine and so well controlled that it is smaller than anything an optical microscope can see. And then to magnify, we need only do this. We place a sample in the way, a small sample or a large one, up to a fraction of an inch, as you will see, and we move the beam back and forth rapidly in a television style. for every position of the beam, there's a position on the television tube, the face of the cathode ray tube, timed to it. And the image, therefore, always fills the cathode ray tube. But sometimes the beam of the electrons is only moving back and forth over a tiny distance, then we have a high magnification. Sometimes the beam of the microscope is moving back and forth over a large distance, then we have a small magnification. And Miss Hardy, by turning one knob, can vary the magnification from a very modest one of 10 or 20 up to 50 or 100,000 in perfect circumstances. What we do is collect the electrons that come off at each time by a collector over here, and that simply picks up all the electrons come from this point, displays them at one point on the screen in the right time, then the next instant, and so on, and it traces out, as you will see, the picture by the motion of this beam. Of course, the trick is the strength and fine definition of this fundamental electron beam. Perhaps we should dim the lights now. Would that be a help? Thank you. Of course, to study a fluorescent screen and delicately to explore what's down there, it's necessary to have the light. We begin to, the controls that we have are quite plain. There must be controls to move the object back and forth under the beam. There must be controls to adjust the focus of the beam, how delicate it is, and where the focus occurs in depth, up and down. And there will be controls for the brightness of the beam. Here are the specimen moving controls. These are the magnification controls, the distance of sweeping, and the focusing controls are mostly on the right-hand panel. And the scan is slow, and we begin to see a few things under the machine. Now, while that is operating, we can go ahead to other remarks. I'm sorry about the light. Is that all right? Oh, very good. Miss Hardy is searching in a field which is, the specimen holder is a little disc exactly like this one. This is another specimen holder. And mounted on that is the eye of a needle. And here is the eye of a needle on this piece of clay on the specimen holder. And we will see when we have an image, the eye of the needle well magnified, and the eye of the needle will open up to admit us all. First it will look not very much different from the eye of a needle, and then it will fill the screen, and then only a small corner of it will be in the screen, and then the screen will be quite blank, will be inside of the eye of the needle. And what Miss Hardy is searching now is the field inside the eye of the needle, which at this scale is a very large region indeed, like a voyage to the South Seas, or not quite like that, but like a half-hour's trip. And she's going to find for us, if she can, an object, a very cunning object, which we know was put there by our friends in Cambridge when they prepared the specimen, and which we have seen earlier this afternoon. So this is some sense of how space changes. Of course, even the most delicate artifact, and I hope we can show this afternoon, we're looking for it, a display of perhaps the smallest objects that men ever made in a controlled way, which have been made by the use of this machine and can be looked at only with such electron microscopes in the past year or two, largely by Dr. Chang, Dr. Nixon, and their colleagues at Cambridge. But while we're hoping to welcome back the traveler on the micron and submicron level, we'll consider some of the other units in physics. It's very easy to reveal the unit of time in the most familiar of all forms, the ticking of the second, which everyone knows and recognizes. The metronome. And the ticking of the year, which is not quite so audible, but is very perceptible to middle-aged physicists, and possibly even to very young ones, is the shown here. Here we have a special 1969 calendar, month after month, and day after day. And when a year has elapsed, that has taken us through 30 megaseconds. 1 year equals 30 times 10 to the 6 seconds. Of course, rather approximately, but within a few percent. So every year adds about 30 million seconds, 30 million ticks to time. And this is the sense of time which we have normally. Let us try to divide time in a small way, and again we must use instrumentation. And here Bill has set up, with the aid of some electronic equipment kindly lent us by the manufacturer, DAW, a very pretty device for measuring time. Measuring time in a way which I think we may enter some sportsman-like challenges to members of the audience to try checking against. Here is the arrangement. This is a very ingenious box, which box contains primarily an escapement, an oscillating object in a watch. It is a balance wheel. In such a box as this, it is not a balance wheel, but rather it is an electrical oscillator, which makes, instead of moving mechanically back and forth, sends electrons first one way and then another way through a circuit. So the moving parts are electrons, of course. Only electrons, generally, we can find to move so fast. Now, this box also counts the pulses. Once you tell it to start counting, it will count pulses one by one, very rapidly, and not missing very many. How would you test that it doesn't miss any? Can anybody invent an experiment on the spur of the moment to make that test? Suppose you had two people, you're a little uncertain whether each counted correctly the number of pieces of Christmas candy in the box. What would one check be? Anybody? Yes? Hmm? Give it a... Sorry, I couldn't quite hear you. Yes? Check it several times, but maybe it always makes the same mistake. What else could you do? How suppose you had two friends who sometimes disagreed? Oh, I would get two of them. If they both give me the same count, well, that looks a little better, you know, and I begin to feel there's nothing that one knows about the other. How can they agree in advance on counting wrongly? That's not always a good test, but I must say that's a necessary test. If they disagreed, I should be very suspicious about the device. But if they agree, at least my first suspicion is missing. Now, this object really counts extremely well, and the first bulb lights 1 and then 2 in seconds. Let us watch it go. When we open the first strip, it begins to count, and then if you open the circuit with the second strip, Bill, it stops counting as soon as it's opened. Now let us see what the face of the meter reads. You see, it was 5 seconds. That was about right. It was a slow operation, about 5 seconds. But notice it doesn't stop with seconds. It also counts tenths of seconds, hundredths, thousandths, 10,000ths, 100,000ths of a second. This dial, this lamp, goes from 1 to 2 in 10 microseconds. Now, 10 microseconds is not much time. And let us try that out by allowing someone to try the machine with about as fast a motion as a human being can make. I suggest that you chop through those two when we ask. With a good, hard, swift chop, your hand will clearly, right, first break one, get ready, but not yet. We'll first break one tape, and then we'll keep on moving as fast as it can, break another tape. There's 6 inches between. Now I ask you to guess how many tens of microseconds will the machine be able to catch this fast hand motion. 1, 2, 3, go! Splendid. Well, the machine caught it. The machine says 1,589. Thank you very much. So I feel that we have some sense of how rapidly time can be divided. We can find small units of time with the aid of electronics, as we can find small units of space with the aid of electronics. In both cases, we are studying scale, the scale in which the world is made, which is very different sometimes from the scale that appears directly to our senses. That is certainly a swift machine, and of course, it is a modest, convenient device. The most elaborated devices of this kind can go perhaps 10,000 times or even 100,000 times faster still. It's not very hard to measure a bullet speed on this machine. It's not even very hard to measure the speed of light on this machine, but you have to begin to use some reasonable space. If you want to measure the speed of light in a very small space, this machine no longer will work. But light and fast particles are about its only failings. And therefore, if you want to look for the measurement of short times, very short times, in which sort of laboratory would you expect to look? I think the answer is clear. Laboratories that deal with the motion of very fast particles and of light, because they have the need for very short timing equipment. And that indeed is where much of this material has been developed. So we have been through time and space, and we're hoping to see deep into space, and our next task is to look a little bit at the units of mass. Well, of course, mass is quite familiar to us, the amount of material in an object. This is a reasonable object of a couple of 100 grams. This is a 1 gram unit. And if you want to measure in pounds or stones or kilograms, it's perfectly all right. You must fit each unit to its use. As long as you understand the unit, no harm comes. That's what we're clearly noticing here. Units, by and large, are arbitrary. They're chosen by men to fit their needs. The Lilliputians would have one set. We have another set. What we're looking for are those things that lie deeper than units, like the range within a single quantity. It doesn't matter what units you measure in. A microsecond is a millionth of the time, which is 1 second. Measured in hours, years, centuries, it's still a ratio of 1,000,000 to 1. That is the kind of argument we were making. Now, I think it would be nice to present a ton, and in the act of presenting a ton, we thought a bit about this, and we wanted to make a ton of some compact material, but it wasn't very easy. So we thought perhaps the most interesting thing was to assemble a ton of boys. And a ton of boys looks very much like a rugby scrum, they tell me. And we have a few of the nucleus, and if we could get them forward and form the proper formation, and I can ask for nearby volunteers, and we'll see if we can assemble a ton. That's a good beginning. Can we have some more people? This is far short of a ton. I'm counting 1, 2, 3, 4, 5, 6, 7. 7, very good. I'll count Bill for 8.5, 9, 10.5. All right, very good. I think this is, we've emptied the seats, but that's only half a ton of boy and man that you see before you. Thank you very much. It's a good half ton for Christmas, and it's a rather nice demonstration. You may calculate that many tons do exist in this room, and of course the measurement of mass goes on to planets and stars and the rest. To measure small masses, it's quite easy. We can imagine the mass of anything small, but it's interesting to recall that if you dot the I when you write with an ordinary soft pencil, you're likely to put about 10 micrograms on the paper. You might calculate about how long your pencil will last if you write long essays, and to see if it checks with experience. You can do these calculations. That's the sort of argument we're trying to introduce you to. How are we getting along with field findings, Artie? You found your field? Shall we look at it then? Okay, very good. Let me know as time goes on. It would be a pity to miss that really splendid object. Let me first show then another quality of scale, which is often not seen, which the physicist very much delights in noticing. That's to say, objects take on a very different meaning when viewed on different scales. Their nature requires this. It's not arbitrary. Their nature requires it. And one example which I can give, and which I like because I have some personal experience with it, is the example of a great power dam. The particular dam I have in mind is one which I saw in Ghana a year ago, in the Republic of Ghana on the west coast of Africa. This large dam was built. It cost several £100 million. It took 5,000 men, perhaps, working several years to build this structure, which is half a mile from here to here, and about 500 feet across. A prodigious work of civil engineering. And all persons recognize a dam is a big structure. That's what we think of. But hold a moment. The real point of a dam is not that it is a big structure. It happens to be a big structure because we are small compared to rivers. But the idea of a dam is to place your finger cunningly in the opening in the dike to stop up the water flow. Here is the dam looked at from a very different scale. A map of Ghana. There is what the dam has been made for. Nobody wants the dam. What we want is the lake that stores the water. If the lake were there naturally, we'd be quite happy. It would save all that cost. Here's the lake. An enormous body of water, a couple of 100 miles long. This is 100 miles. And the dam is, on this scale, can hardly be seen. A half mile is only a little dash down here, too small to display. And so you see that from the point of view of the engineer who really built the machine, the dam is a small thing, tiny thing, holding back a great lake. And the skill of the designer comes in exactly that, in deciding how to make the smallest dam for the largest possible lake, and not the other way around. Are we able to see our... Oh, very good. It is, oh, I see, it's beautiful there. But it doesn't appear in the monitor.
No, I think it might be the light still.
Oh, you think? Shall we? Well, I think we can try once dropping the lights to see if we'll produce an image in that way. Yes, I think I can faintly see it. I shall describe it, and then we can look at a photograph of the same object. Perhaps you can faintly see a narrow checkerboard gridwork in the television monitor. The television on the gold monitor there, and I can barely see it in the side monitors. Let us, thank you very much. I will simply mention that these large squares are in reality only 2/millionths of a meter. That's to say, the best light microscope will only reveal a small patch of one of these squares, the best it can do, and the lines which make it up, which are obviously man-made lines. Here is that same object in photograph. Very flat, but an emergency. In photograph, the very same lines are the smallest known artifacts that I think in the whole world. These are about 3 or 4 times thinner than the lines of the smallest lettering that's yet been made, and clearly when we develop sufficient skill to handle this fully, and not only to make ruled lines, but also make all sorts of shapes which can be done electronically, we can imagine printed circuitry of extraordinary smallness and fineness, much better than the tiny pinhead integrated circuits that we saw earlier. And that then is some sense of how hard it is and how real it is to scan the nature of space. And I should like to close by discussing another means of reducing distance. This is a very curious object. It happens to be made, I believe, of sugar. Yes? 'Tis so. And here I see a letter, G-U-L-L-I-V-E-R, Gulliver, and an S for Gullivers. This is a large, heavy object. I think none has seen anyone like it. But there is something related to it, which I believe a good many people may have seen around here. That is an object rather like this, which does say also very much the same thing in a different size. It reads Gulliver's Laws, and it is what I think you call a piece of rock. Now, I leave it as an exercise to the reader, perhaps, to describe how these large letters, which are easily assembled by man's clumsy hands, are made into a solid bar which says Gulliver's Laws on one end, and on the other end has something written in a language I'm not very familiar with. Something like I don't know what it says on the other end. But I hope that somebody will tell me next time, if I tell him that these are 2 centimeters high, if somebody will tell me how this was made in the sense we know it was drawn out, pooled from a piece of taffy, how much reduction was in this area if the letters were to come down, and then what happened to the rest, how long did the piece become? That is a proper sum of exactly the sort that Gulliver had to do, and that, I think, is enough for the hour, except it would be pity to end without recognizing that not only do I get this nice piece of rock, but I think everybody can have one. So a few people perhaps will come forward and try a sample and see how it works. Just as you like. Yes, it's just what you're eating there. That's the beginning of it. That's how it's made.